Okay, any last minutes about alkynes? Or any last questions, sorry. About alkynes? If not, we're going to move on to the next chapter here in our discussion of more reactions here. Delocalized pi electrons or conjugated double bonds. Okay? So, with delocalized pi electrons, let's talk about some of the effects here we see. All right. So, let's talk about the effect of neighboring double bond on the reactivity of sp3 hybridized carbon. So this will be the allylic carbon atom. Okay, so there's a few properties we'll go over about this specific position. So I kind of alluded to this on the quiz today and last week in lab when we talked about NMR of alkenes. So the first thing we'll talk about is the bond dissociation energy. So the bond energy, or the energy needed to separate a bond and get back the neutral atoms of the bond. Okay, so bond, sorry, not dissociative. I'm not talking about like personality dissociative disorder. Dissociation energy, my bad. All right, so this delta H naught, BDE. Okay, so I'm going to draw a molecule here, and we're going to examine all the different bond energies for CH bonds. So here's an example, cyclohexene. All right, so we have 3 different hydrogen atoms, okay, and on only one of them will be the smallest here. So this bond is considered the allylic position. Okay, so the allylic position is the hydrogen atom that is one bond away from the double bond. So it's bonded to the carbon, that's one bond away from the actual double bond in the molecule. So this energy is actually 360 kilojoules per mole. Now if we compare that to an alkene type, let me just use a different color. An alkene type hydrogen. So a vanillic hydrogen is another name for a hydrogen bonded to a sp2 carbon, which is an alkene carbon. So vanillic is 445 kilojoules per mole. So that's quite a difference here in terms of energy. And then if we have an alkyl position, okay, and an alkyl hydrogen, that is 400 kilojoules per mole. So not as strong as an alkene, but still weaker than an allylic position. So there's something special about this position. There's something special about this hydrogen that makes it particularly reactive. Okay, so here we could write the relative stabilities of radicals. So when we're talking about bond dissociation energies, what we're talking about is the radical stability when that bond breaks. Okay? All right. So That means if a bond is easier to break, the radical must like the form, so it must be more stable. So what would be the most stable radical of all these three positions? Allele, vinylic, or alkyl?
Vanilla.
Yeah, vinylic. Well, no. So which one is which bond is easier to break? So which hydrogen is most easily removed? Allylic, yeah. So allylic is greater than the alkyl. Okay, and that's greater than vinylic. All right, so what we're talking about here is the allylic radical, the alkyl radical, and the vinylic radical. Okay? So imagine we're comparing the stabilities of these three radicals. This one, this one, versus this one. So those are the three radicals we're comparing. So one of these radicals is has a special kind of stabilization. So something happens that helps stabilize this radical, and we're going to talk about. We'll talk about that. Okay. But are any questions on this page? Any question on the concepts here? So the weakest bond will form the strongest radical intermediate, and it turns out the allylic position is the most stable. The CH bond there is the weakest, so it's the easiest to break. So it's that radical forms the fastest. Okay, that means, the less energy it takes to break that bond means the activation energy is less, so it's easier to reach that radical. So it must be more stable relative to another radical, unstable radical. All right. So one effect of neighboring double bond on the reactivity. Okay, so now let's talk about substitutions. Let's go to part 2, substitution. So let's recall that if we had a primary alkyl halide and we tried to use a weakly basic nucleophile, a weakly basic and a poor nucleophile, not very good, we had no reaction, right? It's not reactive enough to do substitution on primary haloalkanes or, primary substrates. SN2 reaction didn't work, right? We saw no reaction in that case. And we also revisited this reaction last chapter. We saw that if you have a haloalkane and it's a vinyl haloalkane, vinyl chloride here, or vinyl halide, this also can't do substitution easily. No reaction. Okay? So what happens here is that if we move that chlorine one carbon away from the double bond, something special is observed. We actually observe a reaction, and it's quite fast. This is a very fast reaction. So we get this product. So we do get substitution when it's a allylic chloroalkene here. Okay. So something must be forming here. So in this case, we talk about the relative stability of a carbocation. So the allylic position, the third one, it's much more stable than the alkyl carbocation. And that is much more stable, or much more stable than a vinyl cation. Okay. Because remember in alkyl groups, when we had like SN1 type conditions, carbocations are favored by increasing substitution around the carbocation. Well, that's not really the case for vinyl, as we saw last chapter. So this is the order of stability here, based on what we've seen. Okay, so there's a few different ways these carbocations are stabilized, and so we'll go over why the allylic position is much more stable. Okay, all right. So that's so we've seen here the allylic position can also participate in substitution reactions. So it's easy. The hydrogen atom's easiest to break. It can participate in substitution reactions where previously we didn't see that for the other kind of similar compounds. And then we're going to talk about, lastly, this affects the acidity here. Okay, so let's draw our cyclohexane again. All right, so now we're going to list the different acidities for these three hydrogens. So this pKa is around 40. You don't have to memorize this, okay? This is for illustrative purposes. This pKa is an alkene. That's 44. All right? Does anyone remember the pKa of an alkane? Let's write it down. It's the highest one I think that's known, 50. So very difficult to deprotonate an alkane. The only way you can generate a carbanion is using a Grignard reagent. So that's the only way. So it sees here which hydrogen is most acidic. The allylic position, or the alkane hydrogen right next to the double bond, right? That's the one. If the hydrogen is twice removed, or 2 carbons away from the alkene, there's a it looks like it's just a normal alkane. So there's definitely something going on here, something in the structure that makes this hydrogen next door to the alkene very special. Okay. So let's talk about the relative stability of a carbanion. So here this would be our conjugate base. Okay. So the allylic anion is much more stable. It's easier to form than the vinyl anion, and that's much greater than the alkyl. All right. All right. Do you want to know why the vinyl anion is more stable than the alkyl? Why would that one be more stable? Do you guys remember about hybridization? Remember what hybridization? Like you have a carbon atom with a hydrogen. What hybridization is most acidic? sp3, sp2, or sp? sp. So that means the negative charge is closer to the nucleus, right? So it should be more stable. But then we see the trend in carbocations. The vinyl cation is the least stable. Well, if you have an empty orbital and it's closer to the nucleus, the positive charge is going to feel the nuclear charge, right? And what's the charge? What's the sign of the charge in the nucleus? Is it negative or is it positive? So think about like what particles are in the nucleus. So we have neutrons, right? Are they charged? No. And there's protons. What's the charge on a proton? Positive. So there's positive repulsion. So that's why it's not more unstable. Okay, so that's the reason. So I just want you guys to realize that. Okay? All right. So we have the acidity here. So we got the trend here. The Lilith cation is somehow more stable than anion, then the vinyl anion, and then the alkyl anion right there. Okay. Are there any questions about these trends here? Okay, so this will explain reactivity, so it'll explain what I'm about to talk about, make more sense. So the question is, why does this occur? Why does this happen? All right? Why is the trend like this? Why is the allylic position so much stable in all three cases? Does anyone have an idea? It's this common thing we have been talking a lot about. We draw these structures all the time. Any guesses? Yep, resonance. That's the key word here. Resonance strikes again. All right, so resonance is the reason that explains these trends, okay? So I want to tell you, any allylic, allylic intermediate, radical, carbocation, or anion, any of these intermediate is stable. Okay, so first let's show the allylic radical. All right, is there a way to move these electrons to make a new radical somewhere? So let's move it this way, move this arrow this way. And then where does the radical go? I'm missing one more arrow. Where should the last arrow point to? Yes, the far left carbon, right there. So that's my radical. So here is a radical. Now let's talk about a carb anion. Yes, what's up? Yeah, so one is pointing towards this bond, making this new double bond here. So this arrow forms this double bond. And then the other arrow coming out of it, that actually points, so this arrow points to this radical here. It gives, it's giving rise to, it's making that radical. So it tells you that the radical is kind of like delocalized or spread out over the whole molecule. All right. All right, then we have, how about the carb anion? How can we draw a resonance structure with this one? So let's move this arrow here. And then this arrow will come up right there. So now the double bond is on the left-hand side. So this will be my carb anion. So reactive intermediate here, that's stabilized by resonance. Okay. Now how about the carbocation? How about this one? How would we make a new resonance structure for this one? Let's move this arrow to the right. Now the positive charge will be on the left-hand side. Okay, so it looks like we have similar resonance structures. It's just the intermediate, like the charge is different, or it's a radical instead of a lone pair, negative charge, or just no electrons at all, the positive charge. So it stabilizes these intermediates. And so that explains why the Delocalized versions of these are all the most stable than the others. Okay. Are any questions on how we draw these resonance structures? So we should be familiar how to draw resonance for these intermediates so we can predict how the reaction will unfold. Okay? Or you know how these how reactions play out. Okay. So next thing I'm going to go over is that instead of drawing resonance structures, we can show how these orbitals look like in a molecule by considering the molecular orbitals of a compound. So I bring this up because later in the chapter, we will have to consider molecular orbitals and how they interact between two molecules and how a chemical reaction comes about. Okay, so here we're going to revisit molecular orbital theory. So MO, or molecular orbitals. Allylic intermediates. All right, so as we progress higher into different chemistry classes, it becomes necessary to talk about MO theory because it explains a lot of things we see in reactions. So, and it's often this theory explains what steric hindrance cannot adequately explain. So we can't always rely on say, oh, it's because of steric hindrance or resonance. So things we rely on, we can't really actually lean on that all the time. All right, so let's start with the carbocation here. So how many pi electrons are in this cation? Or how many double bonds are there? One. So how many electrons are in a pi bond? 2. So this is 2 pi electrons. The reason I bring this up because soon we'll have to talk about something called aromaticity, and it has to do with pi electrons. Okay, so let's be comfortable here counting pi electrons. So pi electrons are any electron that's in a p orbital. Okay, and since all these intermediates can do resonance, all the electrons we see drawn here, the lone pair and the pi electrons, they must be in p orbitals because that's the only way you can do resonance. Okay, so this one, how many pi electrons are in this intermediate? 3, the pi bond and the lone pair, the lone electron that's in a p orbital. So I'll draw these orbitals out in a bit to kind of help you visualize that. So 3 pi electrons. And how about this one right here, where we have a lone pair instead of just one electron? How many pi electrons are in that one? How many? 4. Good. Thank you. Very good. All right. So what's the big deal? Well, where are the molecular orbitals? Okay, so let me talk about this. So you have 3 energy levels. So in molecular orbital theory, there's commonly a series of energy levels. All right. So I'm going to write over here the atomic orbitals. All right, so in this group, what we have here are a series of p orbitals. Okay, so you have 3 p orbitals. All right. When they combine, so the atomic orbitals here are going to combine. They combine to form molecular orbitals. So I'm just going to draw them as p orbitals right next to each other. In reality, they're more meshed up. So they're more like squished together into a fatter orbital. But for clarity's sake, I'm just going to write them as 3 p orbitals close together. Okay? So you have the bonding interaction. When all p orbitals have the same sign, that's called a bonding molecular orbital. Okay? So in each of our cases here, we're going to draw 3 energy levels. And for the last one here, this is called a bonding MO. So if electrons occupy this is a bonding interaction. It forms a bond. It wants to form a bond. It's more stable if you form a bond here. All right, so I only have 2 pi electrons for the cation, so 2 there. And I put 2 also in here, and then 2 also in here. Okay, so this is trying to explain how these orbitals work, okay? So this one right here, so actually let me just put in parentheses, this is a pi bonding orbital because I'm using the p orbital next door. All right, this one is not involved in bonding. It's on the same energy level. So you see how it's kind of the same level of the atomic orbitals. So that's called non-bonding. It has no preference for a bonding interaction or to form no bond at all. It's destabilized. Okay? So that's a non-bonding MO, and we denote this with the symbol N. So that's non-bonding. All right, the next one is the highest energy level. So in MO theory, right, we have usually there's 2 types of orbitals. If you have a bonding MO, and what's the other one called? The one higher in energy. It's the opposite of bonding. So what do we call that? Say again? No, so non-bonding, you might think that's it, but non-bonding just means like it's a lone pair and it doesn't do anything. So what's the opposite of bonding? It's you might think it's non-bonding, but there's a word to denote like opposite. Anti. So that's the anti-bonding orbital. I know it gets confusing. Non-bonding, anti-bonding is an orbital. It's a bonding orbital, but when you occupy that orbital, it actually destabilizes the molecule. So it actually causes the molecule to kind of like be unstable. It's more sometimes a little more reactive. Okay, so that's the bonding, anti-bonding MO. And that's a pi star interaction. So this is a little more advanced. When you get studying MO theory, you'll see energy levels in the MO diagram that says N, non-bonding. So those are usually for where lone pairs are put. Like, for example, this lone pair in my 4 pi electron anion, that's where the lone pair occupies. So it's in the non-bonding orbital. So this molecule is stable because it's still not in a anti-bonding orbital. Okay, so the anti-bonding orbital, remember, this requires energy. So you need plus energy to get to this state. So that's an unstable, process to go from this non-bonding orbital to a higher energy level. Okay, all right. So the reason I write this out is because later on we're going to talk about a particular reaction, and we'll have to consider these orbitals and how they interact. Okay, so that's the only reason. All right, so now let's draw. Let me just erase this a little bit. Now let's draw what the MO looks like for the non-bonding orbital. So when you go up in energy, your orbitals here, they have to switch signs. So I'm going to draw a node right down the center p orbital. So now every time you see a dotted line, that's a node, and the sign of the function or p orbital must flip. All right, so there I have one node. So that indicates there's no bonding happening between those two orbitals. Okay, and then the third one, I'm going to have 3 p orbitals again. But every time you move up a level, the number of nodes increase. So just like, I'm not sure you guys recall like atomic orbitals. As you go higher, like 2s, 3s, the number of nodes increases. So that's like what's happening here. We're going higher energy levels, so the nodes will increase. So I'm going to draw 2 dotted lines to split up these orbitals here. And that's just what the picture looks like. Okay, so these dotted lines, they are that's a node. A region of space, or a region where you're not likely to find the electron to be at all. So that's, and you get that by observing the wave function of the electron, but don't worry too much about that. Okay. All right. So just keep this in mind, this orbital picture. Pi bond, pi MO, N, and then pi star. Okay. So if anything occupies anti-bonding, that molecule is not stable, so it has some instability associated with it, and we'll kind of see that when we talk about benzene in more detail in probably not this chapter, but in the next chapter after this. Okay. All right. So I know that not a little much about MO theory there, but that's how we explain these p orbitals and how we explain this, how they're still kind of stable as molecules. None of the anti-bonding orbitals are occupied here, see? When none of them are occupied by electrons, these intermediates are stable. Okay, that's probably the best way I could put it. All right, so now let's talk about some reactions of these type of systems here. All right, so let's go over the first one. Reactions of allylic compounds. All right, so the first one is we have another free radical halogenation. All right, so free radical. All right, this only usually works for bromination. That's the most common one, so we'll just use that one. So bromination, that's the most famous one. All right. So let's say we have our alkene. So if it favors this alkene here, well, not just this alkene, but an alkene in general. All right, so you need this reagent. So this is as a special name, N-bromo. All right, so this is called NBS. It's not a broadcasting station. N-bromo. All right, so when we name amines, if amine has a substituent, you could just say N dash and whatever's on it. So when we start naming amines, well, we might talk about that. Okay, so N-bromo. All right, and this is called succinimide. Nimide or nimide. All right. So that's the name of that compound here. And what happens here is you have H nu, so light. And this is just the solvent, CCl4. Alkenes are nonpolar, so we should probably put a nonpolar solvent to get everything in solution. And what we observe here, you might think, okay, well, I have a bromine. Won't that just attack the double bond? But it actually doesn't do that. It actually goes and attach itself to the allylic position. So that's how you can get an allylic bromide on there. So that's particularly useful because what if you still need the alkene, right? And you just want to halogenate at the alpha position, one carbon over. That's a useful technique to have here. Okay, plus. All right, the byproduct is the ring structure we just drew, but what's going to turn out to be here is just the, so when this compound has H, where the bromide was, it's just succinimide. Okay, don't worry, you don't have to say that word, but that's this compound, succinimide or succinimide. Okay, all right. But as always, we can write this result, but how does it work? How does the reaction actually take place? So we'll go over that next. So, are any questions on anything I've drawn right here? Any questions so far? Okay. All right. So first thing I have to do is I have to talk about how NBS is prepared, because this will tell us how the reaction actually works here. All right. So let's talk about preparation of NBS. So NBS is actually formed by this reaction. What's Br2? All right. So NBS works by forming, there's a particular reaction that, or a particular mechanism here we'll go over. All right, so you get NBS, and then you get HBr, a trace amount. Okay, so let's go over how this happens, okay? So you take NBS and you treat it with HBr, and it's going to generate a very small amount of bromine. So the small amount of bromine here is the key. So when I say trace here, a very small amount. If you use too much HBr, you're going to generate too much bromine, and that will just react with your alkene. So that's why it has to be trace, okay? So the trace amount here is important. So it's important here. All right, so let's talk about the mechanism. And after I talk about the mechanism, that'll probably be it for today. So the mechanism of free radical bromination. Remember, this is specific to allylic bromide. The allylic position being substituted with a bromine, the hydrogen. Okay? So, first you have MBS. You have a trace amount of HBr. So if I do ask this question, like on a reaction, I will say MBS trace HBr. Okay? All right, so HBr, this will slowly react and be in equilibrium, so it can go back and forth. Okay, so HBr. Okay. H plus. So we still have a BR there. Okay. So it's better if we just we draw a resin structure here. So now the nitrogen has the positive charge. Because nitrogen has a better, remember nitrogen is less electronegative. It prefers the positive charge better than oxygen. So let's just write it this way. This is the better resin structure for nitrogen. Oh, sorry. I meant to draw a single bond. Erase that. O. Let's just write this as an H. Double bond there. We have an N. O. Now this has a Br plus. So when nitrogen is attached to Br, which atom is more electronegative? Is it nitrogen or Br? So which atom is more electronegative, nitrogen or bromine? Close. So actually, it's actually tight. It's pretty close, but nitrogen is actually a little more electronegative. Okay, so it goes fluorine, oxygen, nitrogen, chlorine, and then I think it's bromine. Okay, but you'll get a periodic table. So nitrogen is much closer to fluorine. So this is partially negative, partially positive. So now, bromine, the bromine that from the previous step here can come in and attack bromine itself because it's partially positive and kick off this group right here. So this is a resin structure. And now what we get is, so let me just scoot over here. Br2 plus all right. Now we have a dilemma over here. When you have a nitrogen with a double bond and right next door is an oxygen atom with a single bond, this undergoes rapid isomerization. So remember when we talked about tautomerism? This is going to switch up here. Okay, so the double bond is going to switch, and the hydrogen is going to switch places and belong on this nitrogen atom here. So this is called tautomerism, and that's how that product ultimately forms. Now, why does it do this? Well, a CO double bond is much stronger than a C nitrogen double bond, so that's the driving force. More polar bond, stronger bond, more stable, so the molecule itself is more stable. So you see this a lot too. I mean, carbohydrates, they end up doing this too. And I'm pretty sure DNA in some mechanism or transformation, they do switch bonds around like this. So it's pretty common. Okay, so that just forms the Br2. Okay, so that's how we form a low or trace amount. So we get trace Br2 here. So trace Br2, and that allows this reaction to actually carry forward. So some reactions, it's really dependent on the amount of the concentration. Okay, so that was just forming the Br2. You actually don't need to regenerate this mechanism. I'm just showing you how it forms. So the key mechanism here is the radical steps. So initiation. So let's go over initiation again. All right, so you guys remember what happens in initiation? The Br-Br bond, when we subject that to light or heat, what happens?
Breaks and forms radicals.
Yeah, so it breaks evenly, right? So we're going to dissociate into two bromine atoms, bromine radical. Okay, good. So then this bromine radical, you can kind of think it will do two things. Honestly, I would have thought it would have taken or attacked the double bond, but it actually doesn't. So that's the funny part. I won't say funny, but the interesting part. There's two positions you can attack here. So your alkene So remember previously, I think I know the difference here. Remember in the alkene chapter, we saw a radical reaction, same with alkynes, but it wasn't with Br2, it was with HBr. So that's the major difference. Br2, for whatever reason, it just behaves differently. That's the best way I can explain it, because in both mechanisms, you're using bromine radical, okay? So, bromine radical, so one of the radicals here will approach, and since this CH bond is weak, it actually prefers attacking that single bond instead of the pi bond of the alkene. So, you have one arrow coming out to combine with the bromine, and then try to draw this clear as possible. One arrow is coming out and landing on that carbon atom, okay? So here you get HBr. So maybe the driving force actually is the formation of HBr, which can go backwards and regenerate the whole process again, okay? So I think that's the driving force. Plus the radical here. Okay. All right, but let's look at our final product. Our final product is the the allylic bromide there. So what do you think the next step is? So the next step is going to be, again, propagation. But what is this carbon radical going to grab? In this case. So what do you think this radical is going to attack next? Anyone? Close, not bromine radical. So when you have propagation, just think of propagation like this. You have to extend the radical chain. So if I take two radicals, the chain would end. So what other molecule could I attack to regenerate the bromine radical? All right, I'll give you a hint. It's not HBr. It's actually just Br2 because there's probably going to be a little more Br2 than HBr as this radical reaction occurs. Because remember, radical reactions, they always generate a small amount of radical. So the amount of HBr formed is probably going to be really low. So Br. Okay, so the radical here, we will regenerate Br radical. And yeah, we can't actually attack HBr because we're not grabbing a hydrogen. It'll just go backwards. We want to grab a bromine. So it's going to be grabbing from the Br2. Br plus Br radical. All right, so that's how this product forms. It's a radical type mechanism. So the steps, it should seem familiar to the radical reactions we've seen, but it's just a different take on the radical reactions. All right, so I just wanted to mention this one thing, and then we'll be good to go. Okay, so. When we have these type of double bonds, we have to think about isomers, okay? So there's going to actually be isomers in these type of reactions. So the very last thing we'll do, regioselectivity, okay? Regioselectivity of free radical halogenation. Of allylic compounds. All right, so there's something called kinetic and thermodynamic control. Okay, so let's say we have our alkene, okay? We have NBS. All right, so guys, if you write, when you're doing, if this is like on a synthesis type problem, you don't have to draw this molecule out all the time. You can just write NBS if you're doing allylic halogenation. Okay, so you get two products. One product is in 30% yield, racemic. This is considered the kinetic product. All right, and then you get a mixture of two different internal alkenes. So you get this one and Br. Since this is a radical intermediate, you can rotate around the bonds. So you get 70% mix of cis and trans diastereomers. Okay, this is the thermodynamic product. And next time I'll explain exactly how each of these products form and when you can expect to get one product versus the other. We can actually control this by temperature of the reaction. Okay? All right, that'll be it for today.